Hey everyone, welcome back to Calculus 2. This will be lecture 25 of the course, and in this section we're going to continue exploring different tests for convergence of series. And so let's jump into it. And we're going to call this section 4.4 comparison of series. Okay. Now, up to this point, the convergence tests that we've looked at so far, a couple of things have had to be true. So first of all, the terms of the series have needed to be fairly simple, right? So far, one, the terms of the series have been simple. We'll say simple, but fairly simple, right? So a little bit of variation there, but so far the terms have been fairly simple. Additionally, and more pressing of an issue is the fact that the series that we've looked at, the tests that we've looked at so far have needed to have special characteristics. Right? So the series have required special characteristics in order for any test to be applied. In order for a test to work, basically. Right, so, example, right? So like the integral test, for example. For that test, we require the series to be the terms of the series to be positive, decreasing, right, etc. Right, so positive, decreasing, etc. Right, there were a couple other things as well. So that's kind of a little bit of a general test. It's meant to be a general test, but even so, there are certain characteristics that have to be true of the terms of the series in order for the integral test to even be applied. It's a fine test if these things are true, but it requires a fair amount. Other example would be like the geometric series. We know exactly when a geometric series converges, but in order for us to be able to say anything about that type of series, it has to be a geometric series. So the form matters here. And the same is true for the p-series as well, right? So the form matters. Right, so a lot of times a series will be nearly geometric or nearly a p-series or nearly appropriate for, integral test or seemingly appropriate, but not quite. Right? And so in these instances, it's useful. The tests that we're going to develop in this section will be very useful. Right? So just to explore that issue a little bit, right? Let's explore it a little bit more. Let's call this an example. If we talk about this series, n equals 0 to infinity of 1 over 2 to the n, right? Well, this is geometric. Right? But just changing it a little bit, and putting an n on the top instead. Right? So this we can talk about. This we know exactly whether this converges or not. But this one, so far, we don't really have a good way to deal with this one. Right? And it's very similar to this, but it's not quite. Right? Another example would be, like a p-series. So if we have like n equals 1 to infinity of 1 over n cubed, right? This is p-series, but we can change it ever so slightly. Instead of just 1 over n cubed, let's make it 1 over n cubed plus 1. Right? But this is not, right? Right? So our previous p-series knowledge would, be fine over here and helpful, but just change it a little bit, add a 1 to the denominator, and the p-series kind of no longer works. Right, and then an example would be, for like the integral test would be, if this is the nth term of our series, n over n squared plus 3, we'll say, squared. This is easily integrated. All right, it's easily integrated, right? But you know, if we just change, you know, the numerator just a little bit and make it an n squared, it's not easily integrated. Right, so these are just 3 examples, right, where you have particular form, change it a little bit, and it doesn't work. Right, easily integrated, right, meets all the the criteria of the integral test, right? It's positive, it's generally decreasing, the numerator is going to grow faster than the denominator, right? So you can see all these things would work, and we could integrate this one, but just throw this square term in the top, you know, just make the n squared instead of just n, and we can no longer use the integral test, right? So what we want to do in this section is we want to what we're going to do is take a look at tests that are somewhat more general, right? So in this section, we want to look at tests that are more general. Okay, and so let's do that. Okay, so this is a very general test, this first one that we'll talk about here. We'll call this a theorem, and we'll so first of all, we've got the sum of a of n and the sum of b of n be 2 series with, you know, 0 less than a of n less than or equal to b of n, you know, for all n. Okay, so that's pretty simple. You got 2 series, you got this sum of a of n, and the sum, these are, you know, obviously infinite series, and the sum of b of n, and they have this relationship to one another, right, where the a of n series is less than or equal to the b of n series, and the terms are all positive, right? So that's a pretty reasonable statement. So the terms are all positive, and a of n happens to be smaller than b of n for all n. Now, if this is true, then, you know, this is going to be very, very obvious to a lot of folks, I assume, hopefully. But you know, if not, I think we'll probably try to prove this one. But the following is true, right? If the sum of you know, n equals 1 to infinity of b of n, right, the larger series, if it converges, then sum n equals 1 to infinity of a of n converges. Right, so hopefully that's intuitive, right? So basically, if the series with the larger terms converges, then clearly the series with the smaller term must also converge, right? So that's very simple. We'll see how we can use this in a moment, but like this is almost like just pure logic, right, on the face of it. The other thing that we can say when we have this relationship, 2 series bn being larger than an, greater than or equal to an, is that if an diverges, then bn must also, right? It's larger. Okay, and so that's a pretty general. This is a very general theorem. Now notice it says nothing about the form of the series. This doesn't, you know, these are just general series. It has a requirement that the terms be all positive, you know, strictly greater than 0, and this relationship between the 2 series. So if you can establish this relationship and you know something about one or the other, then it implies something, right? It implies something about the other series. So let's prove one of these. Let's prove statement 1. Okay. So the assumption here is that b of n converges. Okay. And of course, a of n and b of n have. So we'll assume that the sum n equals 1 to infinity of b of n is equal to some L, right? So some sum, and that 0 is less than a of n but less than or equal to b of n. Okay, and then let's basically pull out an nth partial sum. So we'll let s of n equal, and this is just labeling, but a1 a2 plus dot 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 plus a of n. So when we say s of n, we're talking about the nth partial sum of the A series. Okay. Well, so because of this, because of the fact that the A terms are all positive, we can say that the nth part, the sequence of nth partial sums is non-decreasing. So because 0 is less than a of n for all n, right, we know that the series S1, S2, dot dot dot, Sn is non-decreasing, right? Because you're adding a positive value to each of these, right? So this would be just the first term. This would be the first term plus the second term, right? And so on. And each time you add another term, you're going to increase the value of S, of the S sub I, right? Okay, so what do we know then? We know that the sequence Sn is monotone increasing. Okay, another word for non-decreasing, right? Meaning it's monotone increasing. Okay. Now we also know that a of n is less than or equal to b of n for all n, right? And so what does that tell us? Well, because a of n is less than or equal to b of n for all of n, the sequence S of n is bounded above. What's it bounded above by? Well, I mean, it's got to be bounded above by this, right? This sum is going to be larger than the a of n sum, right? And this one is equal to L, right? So that means S of n, it must be bounded above by L. Okay, so that's just a consequence of the fact that the terms are all smaller. The A terms are all smaller than the B terms. Okay, that's going to mean that the nth partial sums, that sequence is going to be less than or equal to L. Okay. Okay, and so what does that imply? So monotone plus bounded implies what? Convergence, right? This is one of the big takeaways from our entry into series, right? Or into sequences, was that if you have a sequence that's monotone and bounded, right? In this case, monotone increase and bounded above, then this sequence here must converge, right? And so if the sequence of nth partial sums converge, then the series must converge. Okay, so to put that a little more precisely, we know that the limit as n goes to infinity of S of n, well, we know that that's going to be equal to the sum n equals 1 to infinity of a of n. Okay, and that's going to imply, since this converges, that's going to imply that basically the series converges as well. It's less than infinity, right? Okay, so it may not be L, but it's no larger than L, right? Whatever this converges to, it's less than or equal to L. Okay, and so that establishes the first part of this theorem. The second part is real similar. It's going to use the fact that a monotone decreasing fact. It's going to use the bounded principle plus the monotone principle, right? And it's just going to be in the opposite direction. Okay, so I'll leave that to others, but That's the basic proof, right? It's relative. It's pretty much, it's, you know, a quick application of this fact right here, basically. Pretty straightforward. Okay, so how can we use this this comparison theorem, right? So how, in practice, what can we do with this? All right, let's do some examples. So the first one we can look at is this: does n equals 1 to infinity, the sum from n equals 1 to infinity of 1 over 2 plus 3 to the nth power, does this converge? You know, when I ask does it converge, what I mean is, does it converge, does it diverge? You know, what can we say about it? Well, this looks similar to like one of the series that we looked at earlier, which is, you know, the terms here are similar to just 1 over 3 to the n, right? Right, and what is this? Well, we know this is a geometric sequence, right? That these terms would be a geometric sequence, and that series would converge. So we know that the sum from n equals 1 to infinity of 1 over 3 to the n converges. I is less than infinity. So what can we establish the relationship between a of n and b of n? So think of this as like our a of n. So a of n is equal to 1 over 2 plus 3 to the n. And this is less than 1 over 3 to the n, which we'll call our b of n. Now, is this true for all n? For sure, right? The numerator is identical. The denominators are identical, except for this one happens to be 2 larger in every instance. So if the denominator is always just a little bit bigger, then a of n will be less than b of n. Okay. So that's true, right? And then, you know, we can say this is true for all n greater than or equal to 1. Okay. And so, you know, we know that b of n converges. Okay. We know that, I'll just write converges. We know that this series converges, the b of n series, the geometric series converges. So that implies that the other one converges as well. Right? So it implies that the other one converges as well, i.e., right, it converges, right? Just by comparison, right? We know that a similar geometric series converges, and because of that, and because of the fact that, you know, this is true, right? Those two facts together imply that this guy here must converge also. Okay. So extremely straightforward, right? Like this is, you know, it's not a geometric series in itself, but because its terms all have a relationship to a geometric series that we can easily identify, and we know something about its convergence, we can use those facts together to, you know, force out the fact that this guy must converge. Okay, let's do another example. Does the series n equals 1 to infinity of 1 over 2 plus the square root of n converge? Well, this looks like kind of like a p-series, doesn't it? I mean, similar to the last example. We'd say this series looks it looks a lot like 1 over the square root of n, i.e. 1 over n to the 1/2 power, which is like a p-series, right? All right, but notice, right, so be careful, right? right? Notice the you know, the relationships the terms have. So a of n we'll call 1 over 2 plus the square root of n. Right? This is less than or equal to 1 over n to the 1/2 for n greater than or equal to 1. Right? But what can we say about this? This is our Bn. Right? You know, but we know that 1 over n to the 1/2 power diverges, right? Right. Because this diverges, this p is too small. P needs to be greater than 1 in order for this to converge. But here p is 1/2, so this series actually would diverge. Right, I should put the series on there. This is the series 1 over n to the square root of n, 1 over n to the 1/2 power. So we know that this diverges, you know, so technically this isn't helpful. All right, this isn't helpful. So let's try a different series, right? So it doesn't have to be the square root of n. Let's try a different one. Let's try a different series. Let's try 1 over n. Another p series where p is equal to 1. Okay, let's see. So if I set my a of n equal to 1 over n, I know that that's going to be less than or equal to 1 over 2 plus n to the 1/2, which we'll call our b of n. And this is going to be true not for all n, but for n greater than or equal to 4. Okay. Now, strictly speaking, the theorem does say for all n. You know, the comparison theorem that we just looked at. It does say for all n. But the reality is that if you have a couple of leading terms where you don't have this relationship, it's okay. It's really not the leading terms that matter. If the first 100 terms, the relationship isn't true, but then you can show that that the 101st term and all of the terms that follow all have this relationship, then you can still apply it, right? And that's because the first 100 terms are certainly going to be finite, and so the convergence of the series is not going to hinge on the first 100 terms. It's all of the infinite terms that follow it, right? So what's important here is not that it be true for all n, but for some n that you can identify, right? And so in this case, we can see that the first term, a1, is just 1, and that's greater than, you know, what you would get here is 1 over 3. And for a2, you'd get, what, 1/2, and again, greater than 1 over 2 plus the square root of 2, which is b2, right? So I'm just plugging in 2's in, you know, for both of these, right? And you can kind of see this. And then you've got 1/3, which again is also greater than 1 over 2 plus the square root of 3, which would be your b3 term. Now, when you hit a4, the fourth term, this is 1/4, and here something switches, where you actually get 1/4 is less than or equal to 1 over 2 plus the square root of 4, which is your b4 term, right? This would be 1 over 2 plus 2, 1/4, right? So here they're actually equal, and everything after this, you know, 1/5, everything after this is going to be going to work out for you. 1 over 2 plus the square root of 5, which is b5, right? And so you could pull out a calculator and check this, but you'll see that this is true, right? And then so on. It follows that these are always the case. Now, you could select a general n and confirm this more. You could confirm this with more rigor, right? But just kind of take my word for it at this point. But yeah, definitely take the time, you know, after the lecture to, you know, set aside, 15 minutes to like figure this out, right? But basically here you've got AI greater than BI, right? But it's only the first 4 terms, which is a finite number, right? So the convergence of the series doesn't care about the first 4 numbers, the first 4 terms. What really matters is what comes after that, right? And so we can apply the theorem. Okay, we can basically apply the theorem because of this. Okay, and so we know then that the series, what we're interested in is n equals 1 to infinity of 1 over n. This is a p-series with p equal 1. And so it diverges. All right, so this diverges. Now notice, this guy is going to diverge as n goes to infinity. It's smaller than this one, right? So that's going to imply that the b series will diverge as well. Okay, right, so if this one diverges, then this one must also diverge, right? Specifically because this relationship right here, right? The denominator is going to grow faster here than it is here. Okay. All right, very good, very good. Let's see what's next. Now sometimes a given series will closely resemble a p-series, or a geometric series, but it may not be possible. Like in the previous examples, we could establish kind of a term-by-term comparison, but in some cases it may not be possible to establish that comparison. All right, so let's write this down. So sometimes a given series will closely resemble a geometric p-series, but we cannot establish the term-by-term comparison. Right, so sometimes they may be similar, but for whatever reason we're not able to establish the term-by-term comparison. And remember, that's what the whole previous theorem depends upon, right? Being able to establish this 0 less than a of n less than or equal to b of n for all n. And you really could augment this and say for all but a finite number of n. Okay, and so if you can't establish this, then you can't quite use the previous theorem, right? So here's where another test comes into play, which is also very general. Okay, so another very general test, right? And this one is called the limit comparison test. Okay, so what do we say here? So suppose a of n is greater than 0 and b of n is greater than 0. So again, two series with non-negative terms, right? So positive terms. So suppose this is true and that the limit as n approaches infinity of the ratio a n to b of n exists, right? So you've got two series, the A series, the B series, and the limit of the nth term of the series A divided by the nth term of the series B is L. Where, and then this is important, where L is finite and positive. All right, so obviously finite, but also positive, okay? Well, then what can we say? Then, sum of a of n and sum of b of n either both converge or both diverge. Okay, and so sometimes when you see a theorem, you can easily, like I think the previous theorem was very obvious what was happening there is all based on the relative size of the terms, and the fact that one converges implies something about the larger or smaller one. And so here it's a similar kind of general sort of like logical test here, but basically, what this is saying is that, look, I mean, if the A series and the B series both grow in comparable manner with regard to one another, right? And this is kind of the technical way of saying that, the limit of the ratio of the two is a finite number, right? That kind of implies that the A terms and the B terms both kind of grow at the same rate-ish, not exactly the same rate, but the same scale. So if the limit of the ratio of the two is finite, right, and positive, then they must both converge or diverge, right? Because let's think about this for a second. Like, if A converged and B diverged, would this be possible? No, right? The A series would, by necessity, grow at a smaller rate, at a much lower rate than B. Right? If this one kind of converged and this one diverged, then the ratio of the two would not equal a finite number in the limit. Right? And then the reverse is true too, obviously. If A diverged and the B series converged, then this would obviously be infinite. Right? If A converges and B diverges, then this is going to probably tend to 0. Right? And if A diverges and B converges, then this is going to tend to infinity. But if instead the ratio converges to a finite and positive number, finite and positive limit, then they must either both converge or both diverge. Right? They have to be doing kind of the same thing in order for L to be the limit. Okay. Now this one has a nice proof. It's fairly straightforward. Somewhat straightforward. Let's talk through it quick here. Okay, so let's assume the conditions of the theorem. So we'll assume that A of n is greater than 0, B of n is greater than 0 as well, and we'll assume that the limit as n goes to infinity of A of n over B of n is equal to L, right? Where L is some finite positive number. Right? So it's non-zero, it's non-negative, and it's non-infinity. Right? So it's some finite positive number. Okay, so these things all taken together imply, right? So this implies that there exists some n greater than 0. Right? Let's call this an n, let's call this a natural number, a positive integer. So there's going to exist some positive integer n such that basically 0 is less than A of n over B of n, which will be strictly less than L plus 1, right, whenever n is greater than or equal to n, big N, right? That's just kind of like the definition of the limit, right? Well, not exactly the definition, but it's the obvious implication, right? Is that if I go far enough out here, there's going to be some n where, I am, strictly speaking, less than L plus 1 whenever I'm larger than that value. Okay. And so we can kind of draw a picture here, a little bit of maybe to aid with our reasoning here. Okay, so if I've got, I'll draw it like this actually. This is my L, right? And say my ratio is going to come down to L, right? I know that it converges to L. This is A of n over B of n. That's this line here. L plus 1 is going to be, whatever L is plus 1. So we'll just put it up here. It's just a larger value. Okay, and so all we're basically saying is that the fact that this ratio A of n over B of n converges to L means that it's going to get ever closer to L, right? Which means that there's going to be some n, some positive integer n, such that, whenever little n is larger than n, i.e. whenever you're out here, you're less than L plus 1, right? So here you can see we're less than L plus 1 Up here we're greater than L plus 1. Here we're less than it, right? So we're just within a, we're just kind of getting this this series into a this ratio into a range here. Okay, that's all that's happening here. Okay, so this implies, right, this piece here, this implies, right, just simple algebra, right, a and b n are both positive values, so this is going to imply that 0 is less than a of n, which is less than, you know, your L plus 1 let's see here, hold on a second, divided by b of n. Actually, I think I have that upside down. I should have an a of n here. A of n here. Well, we'll just do it like this. It's okay. Oh, shoot. So 0 less than a of n less than L plus 1 over b of n, right? So that's the implication there. I think that's okay. Okay, and then what can we do here? Well, we can just kind of pull in the direct comparison test, right? Right, we can just pull in the direct comparison test. So by the direct comparison test, right, by the direct comparison test, if the sum of b of n is less than infinity, then so must be the case of the sum of a of n. Okay. Right, so if you know, if this is a finite number, well, then that means that's definitely a finite number too, doesn't it? Right, and the reverse is you know, can be easily shown as well, right? We could, you know, we could easily extend this argument to include the reverse, right? So similarly, we'll say, so similarly, the limit as n goes to infinity of b of n over a of n equals 1 over L can imply will imply the reverse. You know, and I guess, you know, namely, let's write that down, that the sum of a of n less than infinity, a of n converging, implies the sum of b of n converges as well. Okay, and so that's the basic gist of it. Okay, and so yeah, that's the idea, right? So if the sum of a of n is less than infinity, then the sum of b of n will be less than infinity as well. It's the same, basically the same argument, a little bit flipped. Okay, all right, good. Let's see an example of this. This is actually a test that is used like all over the place. And it's a helpful one, right? So let's do an example. Show, and this will be a nice kind of general example. Show that the sum n equals 1 to infinity of 1 over a of n plus b, you know, where a is greater than 0, b is greater than 0, diverges. Okay. Well, let's consider, you know, consider this guy. All right, this is a divergent harmonic series. Right, we know that this series diverges. It's the divergent harmonic series, right? So this would be like a p series with p equals 1, right? So if this one diverges, then maybe if the ratio of the nth terms of this, you know, is a finite number in the limit, then that's going to imply that this diverges as well. So let me write that down, because that's the trick, right? Because if we find, so because this diverges, if we find that the limit as n goes to infinity of, and we'll just say this is our a of n and this is our b of n, So if we find that this is equal to some L, then the implication is that this will also diverge. Right, so that's kind of the that's the chain of reasoning that we need, that is going to be applied here, right? We know this diverges. Now, if the limit of the nth term of this and our candidate series, if the ratio of those two is has a finite limit, then that's going to imply that whatever this one is doing, this one will be doing the same, right? If this one's diverging, this one will also be diverging. Okay, so let's test it. All we got to do is kind of see if we can work this out. So the limit as n approaches infinity of, we'll just write it like this, nice and ugly, an plus b over 1 over n, 1 over an plus b over 1 over n. Right, we can break this down. You know, we can write it like, you know, basically like so, right? It's just a simple. And this is going to be n over an plus b. Right, we know what's going to happen here, right? We're going to divide everything by n. This will be a kind of a reminder since we haven't done this in a minute. So n over n divided by an over n plus b over n. What do you get? You got the limit as n goes to infinity of 1 over a plus b over n, right? And so this is going to be 1 over a, right? Now a is a positive number, right? That was given up here. A is a positive value, right? So that means this is greater than 0. So this is the limit of an over bn, right? And so because it's a finite positive value, the implication is that the series n equals 1 to infinity of 1 over an plus b diverges. Right? This series must be doing the same thing as this series, and this series diverges. We know this because it's p series, and we can just easily verify that. This series must be doing the same thing, right? Specifically because of this part here. Specifically this part here. Okay. All right. Excellent. Okay. So this limit comparison test is, as I said, is very valuable. It's used in a lot of different places, and we'll use it certainly as we go forward. It works really well when, you know, so the limit, looks like I'm running out there. The limit comparison test works really well when comparing a sort of messy algebraic series with a p-series. Right, so an example here. So like, let's just create some columns here. We got the given series, and an example there might be like this: the sum of 1 over 3n squared minus 4n plus 5. Right, so you got this series and a good comparison series. Right, so you always have to pick a good comparison series, but in this case, you know, something like 1 over n squared. And what would happen here? Well, this one is, you know, this is a p-series. P is greater than 1, n squared, so this definitely converges. And so because, you know, basically if you can recall what happens when you have a limit of rational functions where the highest power, the degree of the two polynomials are the same. This is n squared, this is n squared as well. right? We know that that's going to have a finite limit, and so, you know, this one converges, and so this one will also converge. All right, another example, not quite as straightforward as that one, would be something like this. Right, 1 over the square root of 3n minus 2, and a candidate series there would be 1 over the square root of n. Right, here you got another p series. Here p is less than 1, so this will diverge. Right, and right now notice it doesn't matter if for this test, this limit comparison test, it doesn't matter that the terms have a relationship to one another in the sense like a term by term sense. Right, we don't care if this one's larger than this one. We just what we need to be able to do is identify the limit. Right, so what we need is just the limit as n goes to infinity of your an over your bn, right? Whatever those happen to be. In this case, this is an, we'll say, and this is bn. It doesn't matter if it's reversed, right? But these are both raised to the same power. Namely, these are, you know, 1/2, right? And so we know what this limit will do. We know that it'll converge in the case when you ratio these two, right? And so. Right, so those would both diverge. And one more example would be something like this. The series n squared minus something like 10 over like 4n to the 5th plus n cubed, right? Something like that. And a comparison series there would be, you know, n squared over n to the 5th. Right, now this may not look like a great comparison series, but because it's n squared over n to the 5th, now notice n squared, n to the 5th, n to the 5th, but this guy is really just 1 over n cubed, right? It's another p series. Here p is greater than 1, so it converges, and so we'd be able to establish quickly that this guy converges as well using this limit comparison test. Okay. All right, let's do some more examples. Some, you know, where we kind of come up with some, you know, you start with a tricky sort of algebraic expression, and then you just like apply a p series to it, and you can quickly establish it converges or diverges. So let's say, you know, does the series n equals 1 to infinity of the square root of n over n squared plus 1, does this converge? Well, I mean, the only thing that really matters here for our comparison series is the highest power of the numerator and denominator. So let's compare this with, you know, basically this the series n equals 1 to infinity of the square root of n over n squared, right, which is the same as 1 over n to the 3/2 power, right? Okay. All right. Okay. Now, hopefully that's clear, right? This is n to the 1/2, and this is n squared, and so you can make this n to the negative 1/2 by bringing it down to the bottom, and then you'd add the 2 plus negative 1/2 would be 3/2. Okay, so here in this case of this guy, p equals 3/2. Right? What does that mean? It implies that this would converge. Right, it's going to converge. It's going to be some finite value. So what we need to show then is we need to look at the limit. Okay, we need to look at the limit. So let me flip my page here. Okay, so what is the limit here? Well, the limit we need to compare is, as I just wrote down, a of n over b of n. It doesn't matter which you choose for your a of n, which you choose for your b of n. But in this case, let's go ahead and make the original series our numerator. Right, so the limit as n approaches infinity of, here, the square root of n over n squared plus 1, right? And then instead of writing it as a fraction over a fraction, I'm just going to write it as a fraction times the reciprocal of the fraction, right? So that'll be times, the reciprocal, which would be n to the 3/2 power over 1. Okay, so normally you would have them kind of stacked the other way, but right, and then we can just kind of do some algebra here. And, what do we get here? So this is square root of n times n to the 3/2 power, and so this is n squared, these two. Okay, so we've got n squared. And then in the denominator, of course, you just have n squared plus 1. Right, and so we can see immediately this is the ratio of two polynomials of the same degree, so it's going to, the limit will basically be the ratio of leading coefficients. Right, and so this would be equal to 1. Right, so what's the chain of reasoning? Right, the chain of reasoning is that B sub n series, in this case, was the 1 over n to the 3/2, right? That converges. Okay, that plus what we just showed, that the limit of a of n over b of n, which is the limit of, well, I guess I'll write it. Okay, that also converged, right? N goes to infinity, sorry. I forgot what I was writing there for a second. Right, so the limit as n goes, so the p-series converges, the ratio of our chosen p-series with our candidate series converges, and so that implies that the sum of our given series must also converge. Alright, so here's the chain. So you've got this, check. This we can just know because with the form we know about p-series. We know that. This we have to check. And once we see that that limit exists, then it implies that whatever this one is doing, this one is doing the same thing. So here the series is converging, so this one must be converging as well. Okay? Perfect. Excellent, excellent, excellent. Okay, let's do one more example, and then we'll end this lecture. Okay, one more example. Does the series n times 2 to the n over 4n cubed plus 1 converge? Okay, so kind of a messy series. You've got n times 2 raised to the n power divided by 4n cubed plus 1, right? So one of the things we can do here is, so let's kind of take the, so let's first whip up a candidate comparison series. So really all that matters in the candidate comparison series are the largest terms in the numerator and denominator. So let's use n times 2 to the n in the top, right? Because both of those will be meaningful. But then let's ditch the 1 plus 1 in the denominator. And let's just use 4n cubed in the denominator. Okay. Now the nice thing about this is that this can be, so this will be our kind of our bn series, right? This one. So this one will be our a of n, right? We're going to use the limit comparison test, right? So this is our b of n. Then this simplifies down a bit, and we can write 2 to the nth power over 4, just basically n squared. The 4 isn't important. I don't know why I put that in there, actually. So this would be our comparison. So what can we say about this comparison series? Well, without a doubt, this is going to, diverge, right? The series here, n equals 1 to infinity of 2 raised to the nth power over n squared. This is going to diverge. Why will it diverge? Well, the limit of the nth term is going to be infinite. All right, so if 2 to the nth power, we've already discussed how that is going to grow much, much faster than n squared. Right, so this will diverge. We kind of discussed this previously, but basically we'll say this will diverge because 2 to the n will grow much faster, and I'll underline that even, than n squared. And so that's kind of the the nth term test, right? What we would say is that the limit as n goes to infinity of 2 to the n over n squared is infinite, right? And so that being the case, right, obviously if the terms are getting larger and larger and growing to infinity, then the sum is naturally going to grow to infinity as well, right? So that's kind of an obvious thing, right? So but what we have here is that our candidate series diverges. Our candidate comparison series is going to diverge. So if the ratio of this to our original series, if the ratio of this term of the nth term of this series to the nth term of that series, if that ratio has a finite limit, then whatever this is doing, that's going to do the same, right? That's kind of the takeaway here. So let's compare that. Let's do that work. The limit as n goes to infinity, and this will be an over bn. And sometimes these can be a little messy, but generally you can do some cancellation, clean them up a tish. But let's write it all out so we know exactly what we're looking at. So you got n 2 to the n over 4n cubed plus 1. Right, that's your an. And then your bn is this other guy, right, which is n 2 to the n over 4n cubed, which we said the really important part there is just the 2 to the n over the n squared. Okay. And so a lot of algebra here that'll clean this up. Okay, so just kind of writing it out here, doing a little work. And what do we get? Well, we're going to get, so basically the 2 to the n's will cancel, and you're going to get n cubed on the top. And on the bottom, you'll have 4n cubed plus 1. And so do we know what happens there? Of course, this is two polynomials. You can think of this as polynomials of the same degree, so the limit will be the ratio of the coefficients of leading terms, so this will be 1/4. Okay. Right, so since b of n, diverges, right, which we saw up here, and the limit of a of n over b of n equals L, that's going to imply that the sum of a of n equals infinity as well. So basically what that means is that the series n equals 1 to infinity of n 2 to the nth power over 4n cubed plus 1 diverges. Okay, so we know that that series will diverge because of the test that we just looked at, right? And so this limit comparison test is something that frequently students have problems with because the logic is, it's not as direct a logic as what people are typically used to with these tests. A lot of times it's just check a thing, plug a thing in, check another thing. This is sort of a little bit more involved, right? So first we establish whether the comparison series diverges or converges, and that's just a fact that we need to know up front. And then if this ratio has a finite positive limit, then it implies that the given series will do the same thing as the candidate series, right? So it's a little bit of a chain of logic there that people have to get used to. But just like anything, do a few examples, do 3 or 4 or maybe 10 examples, you've got it. So, all right, that's where we'll end this one. And next time we'll look at what's something called the alternating series, which is a super fascinating type of series. It's got a lot of great qualities. Following that, we'll look at a couple more tests, and then we will be ready to jump into Taylor polynomials and power series. So we're getting closer to the end of Calculus 2. Maybe about 3 or 4 more lectures, I'm going to guess. So, all right, take care.